Welcome to the lecture 24 of Physics 10 in 30 lectures. We start Unit 4, our last unit of the semester, with quantum mechanics, whose strange and weird rules become manifest in observing interaction of light with matter. We will start with an overview of Chapter 12, Quantum Mechanics. The chapter overview covers both the topics we are covering in this lecture and the topics we will cover in the next lecture set. Then, we have a series of borrowed lecture clips from Physics 4C for a conceptual introduction and discussion of the Blackbody radiation and Planck Law as the first successful theoretical description of this thermal radiation, which also introduces a form of our first quantum assumption. All of that leading into Einstein's explanation of photoelectric effect and extension of the wave-particle duality that Einstein introduced for light. Extension of this idea into matter waves by de Broglie. As these lectures are borrowed from Physics 4C, any textbook references here are to OpenStax University Physics Volume 3. The last lecture section in this set, looking at the Heisenberg uncertainty principle, is an old Physics 10 lecture video. So please note that the textbook chapter number appears shifted. What is shown at the beginning briefly as Chapter 13, Quantum Mechanics, is indeed the same chapter as our Chapter 12, Quantum Mechanics. As we spend just this week on quantum mechanics, we will use the next lecture set to look at the semi-classical models and a glimpse of the quantum mechanical approaches to physical systems. For now, we start with the Chapter 12 overview. This is the overview video for Chapter 12, Quantum Mechanics. As we cover this first pillar of modern physics, we are going to focus on the key conceptual ideas in quantum mechanics. So, in section 12.1, the textbook introduces some foundational concepts, talking about quantization, and something called the correspondence principle, which I think I mentioned before. It has to do with the fact that our scientific knowledge so far through classical physics is experiment-based. So the newer theories in modern physics, quantum mechanics and later special relativity, has to reduce to the classical limit when we are in the regime that looks like what we are looking at in the classical physics. So for quantum mechanics, the counterpart is for large objects. That's when the quantum mechanical results should become indistinguishable from classical results. And when we are looking at small, microscopic, subatomic objects, like parts of an atom, that's when quantum mechanical results will become manifest. Both in the textbook and in the lectures, we'll start by covering the key phenomena, which are, as covered in the textbook, the blackbody radiation, covered in section 12.2, the photoelectric effect, covered in section 12.3, and wave-particle duality, I guess covered in section 12.4, the wave nature of matter. So the lectures will cover the details of these phenomena. Let me just highlight one most important thing out of each phenomenon. Blackbody radiation is where we introduce Planck's law and the Planck's constant, one of the three fundamental constants that describe how this universe operates. The other two are speed of light and the gravitational constant, capital G. Photoelectric effect is use of this Planck's constant in describing light in its particle nature. That's covered under photon hypothesis. Specifically, and you will see this in the lecture and the textbook, the phenomenon called photoelectric effect as explained by Einstein, works best when you think of light when it's interacting with the electrons in the metal, the photoelectrons that are being ejected, as a discrete particle with some energy, E, equal to the frequency of light times Planck's constant. It's for this explanation of the photoelectric effect that Einstein received his Nobel. His work on special relativity being too theoretical, at least at the time. Today it's not theoretical at all, as we will talk about when we get to special relativity next week. And the assumption that Einstein made for the photon, light, can be extended to everything in nature. That's where wave-particle duality comes in. The things that we were used to thinking of as particles can be assigned a wavelength called de Broglie wavelength. That's given by the relationship momentum of a particle is equal to Planck's constant divided by the wavelength of the matter wave that represents that object. And this wave nature of matter is demonstrated in the Young's double slit type experiment using electrons and also neutrons, and I'm not sure if the experiment with the proton was explicitly done, but the interference phenomena involving these particles conclusively prove the wave nature of these matter particles. Now, this wave-particle duality of both classically wave phenomenon like light and the classically particle phenomenon like elementary particles, this duality leads to uncertainty principle. And for some reason that's covered under quantum principles in this mind map, so let me get to that. This is the material in section 12.5, uncertainty principle. So the Heisenberg uncertainty principle, it sets a limit that is quite foreign in classical phenomena. Classically, we always made the assumption that you could make your measurements as precisely as possible. And the uncertainty principle says that that is not possible, even in principle. For two observables that are related to each other, like a position and momentum r, there's a fundamental limit to the combined precision of position measurement and momentum measurement. That's expressed in the textbook as uncertainty in position multiplied to uncertainty in momentum is greater than or equal to, I guess more precisely, h bar over 2. Sometimes we would say approximately greater than or equal to h as an order of magnitude thing. And you can look at this limit as us paying more attention to measurement. Any measurement process will affect the state of the system, which leads to this uncertainty. And in the lectures, when we look at the matter waves using PHYS simulation, we will also talk about how this uncertainty principle follows from the wave-particle duality of all matter. That once you understand particles having wave nature, then this position, momentum, precision limit is inevitable. Now, this node, probability wave, I think it covers things discussed in one of the later sections. I think section 12.8, the wave nature of matter causes quantization. That's the last section in the chapter. Sort of wrapping up everything we look at in this chapter, including what's covered here under atomic structure. So there's a bit of a history to go through under discovery of substructure. This is what's covered in section 12.6, discovery of atomic nucleus. First, we discover electron as a distinct particle, distinct from atom, that it's normally part of. And with the discovery of the electron, we knew it had a negative charge according to the sign convention we already assigned to the electric charges. And after discovery of that electron, the remaining piece of the puzzle was how the positive charge was distributed, given that the atom is electrically neutral. There were competing theories, something called Plum-Pudding model, and Rutherford is one of the people who believed in something called the Saturnian model. So he did what's called the gold foil experiment, shooting alpha rays, which we now know as helium nucleus. So pretty massive object compared to the electron. He fired it at a very thin foil of gold, and you will see a representation of that in one of the lecture videos using the simulation. And the result of his experiment could only be explained through existence of something called the nucleus, a very small region of atom that contains all the positive charges and most of the mass of the atom, like more than 99.9% of the mass of the atom. And it's in trying to explain how this nucleus and the electron existed in an arrangement that we would recognize as a stable atom that the Bohr model comes about. So the main challenge here was that the Plum-Pudding model was out, and what was called the Saturnian model that had the electrons orbiting around the nucleus had this theoretical problem with the stability of that arrangement, because when an electron is in an orbit, it's undergoing centripetal acceleration, and an accelerating charge emits radiation, and that radiation being emitted means it's losing energy. So in order to explain the stability of the atom, and also to obtain an agreement with the observed spectrum of hydrogen, which has already been well studied by chemists and people working with atomic spectra, Bohr suggested a model that involved quantized orbits that's quantized by discretizing the angular momentum. So he proposed that angular momentum of the electron can come in only in integer multiples of h bar, or h, Planck's constant, divided by 2 pi. While one might ask, why such a rule? Well, this rule does predict the correct energy levels that will correctly predict what we see with the hydrogen spectrum. And as I will mention in one of the later lectures, this is one of the fundamental quantum assumptions that we carry over even to the more advanced, the actually correct view of quantum mechanics. Because almost everything we are covering this week, it's a semi-classical models, semi-classical view of quantum mechanics. So some aspects of it will be wrong. But I will distill 3 key quantum assumptions that those of you who major in physics will continue to see in your upper division physics classes. And one of those quantum assumptions is the angular momentum quantization that's first introduced in the Bohr model. The other two relate to the photon hypothesis and the de Broglie wavelength. So that's section 12.7, Bohr's theory of the hydrogen atom. Now that covers all these sections, but in this mind map, for some reason, the applications are split off to its own node, branch. So what it covers is electron microscopes. I think that's covered in section 12.4, the wave nature of matter, and light meters and solar cells. That's mentioned in the photoelectric effect, section 12.3. So that's everything covered in this mind map and in the textbook. As I said, we'll focus on the key conceptual ideas, both in the textbook and in the lectures. And in the homework, there will be some questions where you have to plug in some numbers, but the formulas that you plug in numbers to will again focus on these key conceptual ideas. All right, does everyone here remember how to use diffraction grating? So before I turn off the light, this is how you should be holding it, horizontal wise. Put it right in front of your eye, and I'm going to ask you to look at that after I turn off all the other sources of light in the room. Maybe I should actually just turn this off. Yeah. So this is an example of what's called blackbody radiation. And what's easy to miss when you are looking at blackbody radiation just on its own is that it looks red. It's easy to think red is the only color there. That's why you have the diffraction grating. Look at it with the grading and see if you can locate the diffracted light. So, as you look at it straight, you shouldn't see anything strange. But look maybe about, 30, 40 degrees to your right, you should actually see a flame that's kind of in the middle of a spread out thing. Do you see that? And do you see the spread of all the colors? Like, do you see green or blue color in there? You definitely see green, right? Okay, now let me do this. I'm going to turn off the flame so that all you see is the glow of the stainless steel. But, it's going to cool down pretty quickly. I wanted everyone to be ready when I turn off the flame. Everyone ready? Okay. Let me turn off the flame. So that's a blackbody radiation. No flame, just a very hot object emitting light on its own. And as you look at, okay, I don't see blue anymore. Do you see green? Yeah. Yeah, you see green and yellow, right? So what you're looking at, that's a blackbody spectrum. And how many here, anyone still looking at it? Everyone had a chance to look at the blackbody spectrum? So the different colors? Okay, good. So how many here remember seeing an object that glows because, were you still looking at it? How many here remember looking at an object that was glowing because it was hot? Like, that's not the only time you've seen that, right? Where else have you seen that? Stove? Yeah, electric stove. So blackbody radiation is a quite common phenomenon. You see it all the time. I do this as a demo as if it's something that's rare. It's not. And so I think we treat this very briefly. An object that is hot emits radiation. When we do thermodynamics in physics 4b, we talk about 3 different ways of transferring heat. There's conduction, convection, and the final one is radiation. And I know in my class we don't quite spend a lot of time on radiation. In case there are other instructors who do it differently, do people remember what you know about, what do you know about radiation? Like, what factoids have you been told in physics 4b that you still remember?
There's a T4 equation.
There's a T4 equation. So when you, So this is what you might know about something called blackbody radiation already. If not, that's fine. So you have this expression that somehow the rate of power transfer, so I guess a rate of heat transfer was proportional to T4, T to the 4th power. And it's actually called, there's a name for it. I like to give names because that's how you search for things. If you want to search it, it's hard to search for T to the 4. But if I tell you that there's something called Stefan Boltzmann law, which says that intensity of blackbody radiation, so intensity of blackbody, and you remember how intensity was defined, power per area,
is given by sigma. This is the Stefan Boltzmann constant. We'll just look it up. Sigma times t to the fourth power. So this is something that, you depending on your instructor, they may have covered it, they may not have. I know I don't cover it because you don't really do anything with it. But I want you to bring your attention to this now because I'm trying to introduce how we stumbled upon a set of laws of physics that we call quantum mechanics. And quantum mechanics has a bit of a traumatic childhood beginning that quite different from special relativity. With the special relativity, I gave you some experimental basis of special relativity, Michelson-Morley experiment, but I hope everyone remembers me saying this. I told you that that experiment didn't affect Einstein at all. Einstein was a theorist. He came up with the special relativity kind of theoretically. This was the set of rules that made sense in the world where Maxwell's equations were correct. Quantum mechanics is completely the other way. Quantum mechanics is, it finds its origins in experiments. It's specifically experiments that contradicted theoretical predictions. So what you just saw, blackbody radiation, that's one of such experiments that, I guess you could put it this way, that defied theoretical explanation in an attempt to come up with a theory to describe what people saw quite plainly what they could see experimentally. That's where people discovered quantum mechanics, really piece by piece. And what I'm hoping to introduce today that we kind of need for Thursday's lab is the quantum mechanical nature of light. So let me put this on the proper place where, so you saw the blackbody spectrum, right? You have some sense that the blackbody spectrum, it's a range of colors. Let me actually show you a blackbody spectrum. Actually, let me do it this way. Rather than, your textbook has one, but PHYS simulation actually has one that's better, where I can actually change the parameters. So how hot do you think that sphere was? So, take a guess. 1,000 degrees C? Sounds reasonable. People with the physics 4B here, do you remember your physics 4B red hot calorimetry result? Okay, is it at least between 1,000 and 2,000 degrees C? All right, so no more than 2,000 degrees C. All right, so let me use this. This is a simulation that just show you what blackbody spectrum looks like based on the temperature. So if it's 1,000 degrees C, then let's say the temperature might be something around, I don't know, 2,000 Kelvin. So it's actually quite a bit high. Oops, I need to zoom in. All right, so this is what this says the spectrum was. Does that look like the spectrum that you remember seeing? So what you remember seeing is reddish color, right? So, so this is what I was saying, that what you are seeing is not exactly the spectrum. What you are seeing is a kind of a product or convolution of your eye's response function, what your eye can see, and what that emits as light. What that emits as light is actually mostly in infrared. In fact, even if you were to get this as, so this is a little bit higher than oven temperature, which also glows. Even if you got it as hot as light bulb, actually the maximum of intensity will still be outside of visible range. That's why light bulbs are so inefficient and LED lights are so much more efficient. But what you do see here is this feature. So, I mean, you did see red and green color. And if you zoom in enough to the spectrum, you can see, yeah, I saw red here, and I saw green here. And I looked for blue, but I couldn't quite see blue because there was very little blue there. So that's the spectrum you saw. So that's the blackbody spectrum. And people could make this measurement. And I guess they probably had a difficulty measuring infrared. But what they did know was when you have a hot object that's glowing, as the object gets hotter, as hot as light bulb, the spectrum shifts to shorter and shorter wavelength, fact, I don't know if Wien's displacement law, yeah, we definitely don't cover that in 4B. So there's a law that describes something called the Wien's displacement law that says the product of the wavelength and the temperature is somehow constant. So people have been studying this blackbody radiation for quite some time. And this kind of spectrum was, experimentally speaking, well known. That, so you have a spectrum that has a local maximum. So if you go to a very long wavelength, and then the intensity there is gets smaller and smaller. But also, when you go to shorter wavelength, the intensity also gets smaller eventually. And there were theorists that were trying to explain this, because this is the picture you have towards the end of the 19th century. You have a complete description of electricity and magnetism in the form of Maxwell's equations. People understand now that light is electromagnetic radiation. And you have development of thermodynamics based on like kinetic theory of molecules. So, and you have atomic theory that's developing. So people understand that when you look at an object like this, it's made up of charged particles, electrons, and that when it gets hot, that there are electrons oscillating around. That has a lot of kinetic energy. So they understand, they can get a kind, so this is the kind of thing that they couldn't have imagined describing in Newton's time. Because in Newton's time, they look at this ball, they have no idea what it's made of. By the end of 19th century, it's within their grasp. They can say, oh, it's made of charged particles. As they get hotter, they oscillate. As they oscillate, they emit electromagnetic radiation. So they feel like they can actually develop a theory to describe this theoretically, not just experimentally. And that's where they ran into problem. Now, I want to see if, does this let me show Rayleigh's prediction? I don't think it lets me show Rayleigh's prediction. So I guess I'll just have to draw it. Let me just draw it. So I'm not going to do the actual derivation, mainly because I can't. But I'm also not going to do it because it's another description of a theory that turned out to be wrong. So, well, I mean, it's a theory you know now, but so this is a prediction of something called Rayleigh genes. How many here are familiar with the name Lord Rayleigh outside of Rayleigh criterion? It's the same Rayleigh. How many here know, have you heard of the phenomenon called Rayleigh scattering? No? You guys never asked the question, why is the sky blue? Yeah, the way it's explained is through Rayleigh scattering. As the light comes, the light oscillates the electrons, and that oscillating electron is like an oscillating dipole. It has a frequency dependence. It happens better at shorter wavelengths. So the scattered light has more blue color in it than red. That's why the scattered light looks blue. And near the sunset, when you look at the light that has come through the atmosphere, the light that hasn't scattered looks redder. Right? Like you cover this sometimes in like middle school science classes, right? In these qualitative terms. And in upper division physics, you might actually do the derivation, but I won't. It's the same Rayleigh. So he's known for doing that kind of derivations. So he and, I don't know who Jeans is. So it's called the Rayleigh-Jeans law. It describes a prediction of electromagnetic radiation from a hot object, a blackbody radiation. And here's a part of the prediction they do get correct. They do get correct that as you go to longer wavelengths, the intensity of the radiation would die off, that it would go down. And you can understand this. Do you guys remember seeing that oscillating dipole simulation I showed and how the amplitude of wave changes depending on the frequency? Did I show you that? Maybe not. Okay. Let me quickly do that just so that you have some intuitive feel for it. So, to do it properly, it would take a lot of math. But I can just show you a quick simulation so that at least you have some sense that it's intuitively correct without going through a bunch of complicated math. Radiation. Radiating charge. This is the one. So I can set this charge to go in a circle. That's the one I like the best. Let me make the amplitude kind of small. And so this is sort of the magnitude of the radiated wave. And if I want this to be larger, more intensity, then I could make the amplitude of the oscillation itself larger. Or the other thing I can do is I can increase the frequency. So the electromagnetic radiation is a result of accelerating electric charges. So when it's oscillating more quickly, it has greater acceleration, so it emits more radiation. Intuitively, that makes qualitative sense. That if I have a charge that's oscillating a lot more quickly than another charge, then it would be emitting away more electromagnetic energy. Yes. Yeah. As long as it makes somewhat intuitive sense, like saying, 2 is greater than 1, then let me just move on from there and not try to prove how 2 is greater than 1. So Rayleigh-Jean's law predicts that portion okay. It says longer wavelength. That means a smaller frequency. It says that longer wavelength, yes, less intensity of light emitted. But where Rayleigh-Jean's law fails is when you run the calculation for shorter and shorter wavelength, this is what Rayleigh-Jean's law predicts. You can find this figure in the textbook. Just keeps on going up without limit. There is there's no known physical effect that Rayleigh and Jeans could consider that would force this intensity to come down at the high frequency range or shorter wavelength range. This acquired a term that actually people use even today in different contexts. This is called ultraviolet catastrophe. I mean, catastrophe makes it sound like it's a terrible thing. Well, it's a terrible thing for theorists. It's a terrible thing for the theory. Because what theorists would predict is that if you see the oven here, right? If you open up an oven, what the theory predicts is that you will be blinded by bursts of gamma rays from the oven, or X-rays, or ultraviolet rays, whatever. Now, it doesn't actually happen, so it's not real catastrophe. It's the catastrophe for the theorists who were predicting something that doesn't happen. But so that was quite a puzzle, and a lot of people have worked on it, and it really came down to there is no known law of physics that would lead to this limiting behavior. It really came down to there is no known law of physics that would lead to this limiting behavior. So the solution to that, the solution to this problem, solution to this ultraviolet catastrophe, is proposed by a German physicist named Max Planck. I guess he must have been fairly there in Germany. There's a bunch of institutions called Max Planck Institute. How many here from Germany? Never mind. Max Planck is the guy who suggested a solution to this ultraviolet catastrophe. And I want to just present his solution and sort of redrive some of these things that I think we can do from that solution. So let me put it this way. So blackbody radiation, I'm just going to write down ultraviolet catastrophe, which results from Rayleigh-Jean's law. I'm writing down all these terms because I'm kind of going through fast and I'm not really doing thorough coverage of this. If you're interested, you can Google search and read, or you can read the textbook. So let me start out with Max Planck's solution to this ultraviolet catastrophe. So let me start out with the result. The result that he derived, you can find it in your book, chapter 6. Blackbody radiation. So, read through it. And this is the plot you're seeing. This is describing Wien's displacement law. Wien's displacement law. Stefan Boltzmann law, whatever. So those are all experimental laws. People were just finding those experimentally because blackbody is common, easy to measure. You can discover all those things experimentally. So where people were running into the problem was, how do you actually understand this? And the Rayleigh-Jeans law, the first attempt at it, failed because it resulted in ultraviolet catastrophe. So the question was how to handle the short wavelength or high frequency case. And this is the result. This is a Planck law for blackbody radiation. That's what they derived. And in order to derive this, I will write it down on the board. In order to derive this expression, I'm putting this on the board because that's the one expression I don't have memorized. Everything else memorized. So to derive this, Planck had to make an assumption. So this is Planck's assumption. He assumed this way. So when you have this object which is radiating electromagnetic radiation, you can think of it like this containing some hypothetical oscillators. As in, imagine you have, I'm just drawing it schematically. Imagine I have some electron here, which is going to be vibrating back and forth, and as it vibrates, it emits electromagnetic radiation, right? So this is my oscillator. It's kind of a model for this object. And it's a model that's meant to be widely applicable because blackbodies are quite common. Our sun is a blackbody. You are a blackbody that emits something like a 10 micron wavelength infrared radiation. Yes?
Can we define blackbody? What is the definition of blackbody?
Well, technically, blackbody is an object with an emissivity of 1. That's the perfect blackbody. But blackbody, in the sense I use the term, as in something that's at some non-zero temperature, so it emits thermal radiation. Everything is a blackbody. I guess atoms? Okay, I guess a single atom is probably not a blackbody. But any macroscopic object is a blackbody. Yeah? So those blackbodies are made up of an oscillator. And this is what Planck assumed. He was trying to just come up with a solution where something would limit the amount of energy that can be emitted at the high frequency limit. So he assumed, okay, this oscillator, it can only have energies in discrete units. And he said this discrete unit of energy, so the whole purpose of introducing this mechanism is to limit the amount of energy at the high end. So you say this discrete unit is equal to, it's proportional to frequency. So that's an important part. And at the beginning, what he did was, well, it's proportional to frequency. So let's say here's a constant of proportionality. And this, I guess, I don't know, when he initially started the derivation, unless the myth I heard was that he was hoping this would cancel out of the derivation. Like when you do any kind of classical mechanics with the mass, you have masses in there already, hoping that it'll cancel out when you're dealing with the gravity, right? So, but this constant of proportionality didn't end up canceling out. And this is what is today we call Planck's constant. And it's one of the, one of 3 fundamental constants of nature: gravitational constant, speed of light, and Planck's constant. Planck's constant. But so that's the assumption he made. You can think of it like, I like a money analogy. Imagine someone said this. So, whatever money you have in your bank account, let's say you can withdraw it all. And let's say they told you the only denomination you can take is a dollar bill. Can you take the entire amount of money in your bank account? Close to almost the whole amount, okay? What if I told you you could only take it in $100 bills? maybe depending on how much money is in your bank account. Now, what if I told you, you can only take it out in the denominations of $1 million bearer bonds? Most of us can't take any money out. So that's what this is. That's what the mechanism here is. As the frequency goes up, the discrete unit of energy this oscillator can have gets limited. So at low frequency limit, this limitation wouldn't amount to anything. So Planck was looking for two things. One, agreement with Rayleigh-Jean's law at low frequency. And this kind of accomplishes that because this at low frequencies, this limitation has no effect. It's like somebody forcing you to take your money in dollar bills. Because it's a lot of dollar bills, but you can take all your money that way, close to all of it. But he was looking for at high frequencies to disagree with this, to force the intensity to go down, and this assumption would force that to happen. So it's a bit of an ad hoc assumption. Like if someone were to ask Planck, like, why did you assume this? His only answer would have been, well, it gives me the correct answer. The correct answer being this. And I guess I don't have a lot of time. Let me demonstrate the correctness of that answer. Let's see, does it do the plot? Okay, they do a plot. So if you want to plot it, you can plot it on your own, put it into Mathematica. And if you just want to plot something numerical, you can just set HC all equal to 1, KB, T all equal to 1, and just let lambda be whatever. That'll be it. What I want to use our time for is I want to show you that, it says it's a left exercise. Let's try it and see if I can actually do it. So this is the intensity as a function of wavelength. This is a result that we are hoping for. So if we take this intensity as a function of wavelength, and here's one of the experimental laws we know. We know Stefan Boltzmann law, and the second one that's in the book is the Vince displacement law. Let's see if so Rayleigh-Jean's law is clearly, it doesn't agree with the Stefan Boltzmann law because it predicts infinite intensity at any temperature. So let's see if Planck's law will give the correct, agree with the, let's see if a prediction of Planck's law will agree with the Stefan Boltzmann law. So what we are hoping is that when you take the intensity, and I'm hoping they gave me the correct expression for doing this, integrate it with respect to wavelength, with wavelength going from 0 to infinity. I'm hoping the result I get is proportional to t to the 4th power. Yeah? Okay, before I start on that, let me make sure I have correct units. For this to work out correctly, so I'm going to need to have from x equals 0 to x equals infinity. And that'll give you some, I don't know, 6.5. So you can say that, all right, whatever this integral is, this is equal to 6.49. And I have my result. This intensity integrated over all wavelengths is proportional to t to the 4th power. And if everything really works out, this 6.49 times all of this should equal Stefan Boltzmann constant. I guess not enough time to go into photoelectric. Well, yeah, let me do that. I think we've spent enough time on this, so might as well finish it and get the payoff. So let me just take this. Actually, let me take that number times all these other constant coefficients that I didn't actually get rid of. 2 pi times Boltzmann constant to the 4th power divided by Planck's constant to the 3rd power divided by c squared. So I'm expecting something with a unit of joules per meter squared, sorry, watt per meter squared per Kelvin to the fourth power. So hopefully that's what we are going to get. So watt per meter squared, yeah, it is one Stefan Boltzmann constant. Wolfram Alpha is smart enough to know that. Good. So that's it. So that's Planck's law. And what I want to emphasize at this point is that in order to derive this expression, Planck had to assume this. And if somebody asked you, asked Planck, why did you assume this? The only answer he could give was, well, this is why. He doesn't have any a priori reason. This is the contrast to the special relativity. In special relativity, we started out with the postulates of special relativity. We said, all right, these two are self-evident truths, and we'll derive the rest. With the quantum mechanics, at least if you are being historically semi-correct, this is not a self-evident truth. It just happens to lead to the correct result. This is what people call, let me write it down so that you have it. This is what people call ad hoc. It's Latin for, I think, here and there, or it's like as it comes up. It's an ad hoc assumption. And as we introduce quantum mechanics the rest of this week, you will see that's what quantum mechanics is built on. It's built on these foundations of ad hoc assumptions, which are not mathematically very appealing. You know, with the special relativity, you had almost like a search for aesthetics. The Maxwell's equations, they are so beautiful, you want them to be right. So for those to be right, the postulates of special relativity has to be right. With the quantum mechanics, it's going to look ugly because it's going to look like a patchwork of these ad hoc assumptions. Out of those, some pattern will emerge. And in fact, I can start off with one thing. So we said, let's see, how do I put it? So here, this is how I was trying to describe it, right? Planck was imagining these hypothetical oscillators, which he doesn't know very well. So to which he assigns some special property which are not familiar, but which gives the right result. And you know, who's to say what these little microscopic oscillators are like? Who's to say like this isn't really their property? And Einstein is the one to take this idea and actually apply it more broadly. So so we don't have time to go over the whole thing. So this is the base. This is the explanation of something called the photoelectric effect. It's an effect observed when ultraviolet light shines on metal surfaces. They see electrons popping out of the metal surface. I can show you videos and all that next time before your lab, the lecture before the lab. And it had certain features to it that people had a difficulty explaining using classical theory of electrodynamics. And Einstein, actually his Nobel Prize is based on his explanation of this. He didn't get Nobel Prize on special relativity because I guess special relativity was too theoretical. And if you want to get Nobel Prize, you want to do something useful with it. That's why mathematicians don't get Nobel Prize. Well, they get usually Nobel Prize for economics. They get Fields Medal. They have their own prize. And the starting point for Einstein explaining photoelectric effect was this additional assumption. He assumed this. He said, so this is for this is an extension of this idea for photoelectric effect, where there are no thermal oscillators like there are in blackbodies. He said, let's see, how do you put it? So when light exchanges energy with, when electromagnetic radiation exchanges energy with any other object, so when light interacts with matter, the amount of energy that the light can transfer is limited this way. The amount of energy exchanged can only come in units of this, or it can only be some integer number times hf, where this is integer. I guess at first sight, this looks like the exact same thing as this, right? The amount of energy comes in some discrete quantized quantity. The difference is this. This pertains to some unknown object. No one knows anything about oscillators. Light, people have been debating about light for centuries, since Newton's time. There was this whole debate about corpuscular theory of light and wave theory of light. Wave theory won. We are supposed to believe that light is a wave. But when you start introducing this discrete energy, it begins to sound more particular, like particle. You are almost saying light interacts with matter like a particle. So what Einstein is claiming with this assumption is much more broadly applicable to something that we are supposed to know very well. That's why I guess it's Nobel Prize worthy. Max Planck stopped here. He stopped with oscillators. He didn't try to extend this assumption to even more. Einstein took that idea and extended it to things that people thought they understood to explain an effect that we're going to go into next Thursday. And if there's time next Thursday, we'll talk about the Broglie Hypothesis, where somebody takes this idea and extends it even more, applies it even more generally. The Planck's blackbody radiation law is what actually led to the correct prediction. I put quotation around the prediction because it's not a prediction at all. It's something that everyone knew. Planck law is the one that actually fits to the experimental curve correctly. And for this Planck law, he had to introduce a poorly justified assumption. The only justification he had for this assumption was that it gave him the correct result. Really, he had no other justification. And this is the thing that I want you to take away from blackbody radiation. This is the most important thing. Planck's assumption that energy of oscillators. So you treat blackbody. So this is the thing that you saw that was really hot on Tuesday. You treat blackbody as being made up of charged oscillators that can take some amount of energy. You say that this amount of energy that can be in the oscillators, energy of oscillators, come in units of some constant that we now call Planck's constant times frequency. So if it's coming in units of this, the only coefficient that can go here is an integer. And this is what we call now Planck's constant. And it's a very small number that has unit of joule times a second. In your lab manual, there's a value there. For some reason, I can never memorize this number. But it's a very small number. Yeah, I don't think I have electron charge memorized, 1.6 times 10 to the minus 19 coulomb. But somehow I can never memorize this number. But anyways, but this is the main takeaway, that Planck had to assume this to get this correct result that we saw. And what we are going to see today is that, I don't know what the right way to say this was. So Planck was restricting this assumption to these mysterious oscillators, mysterious blackbodies. And it turns out he was not being bold enough. So when you first look at this, it's an assumption, like where's your justification? Turns out Planck was just being way too careful, because it turns out this relationship applies much more broadly. So the first thing we want to look at is something called the photoelectric effect, and I thought I would start out with a video because it's easier to kind of see the demonstration that way. Your lab today is, by the way, photoelectric effect, so you'll be doing actual concrete measurements based on that effect. But there's I found this while I was searching for physics 10 material, and it's actually
We use this natural light instead of the carbon arc we had inside, and we could use this simple electroscope instead of all that elaborate equipment that we had inside. Bill has put a glass plate on the front of it to protect the needle from the wind, and he's wrapped the glass plate with wires to shield the needle from any electric charge that might be on the plate. The wires are connected to the can of the electroscope. And now will you put a negative charge on the electroscope with that plastic rod that gives a negative charge. Here is a piece of lead foil, and if you'd hand me some of the steel wool, I'll get it clean. We'll put it on the electroscope, and of course when I touch the electroscope that discharges it. If you give me the piece of glass and charge it negatively, I'll hold this glass in front of the lead, and there we have a charge. Now I remove the glass, and we see that the electroscope isn't discharging. Now I'll try magnesium. This has to have its oxide removed too, and I'll bend it and put it on here. And now if you charge that negatively, we'll see that it isn't discharging with the glass in place, but if we take the glass away and let the sun fall on it, discharges, put the glass back, we slow the discharge up and take it away, and it discharges much more rapidly. Let's do the experiment once more, this time with the electroscope charged positively with a different plastic that gives a positive charge when it's rubbed. And now when I take the glass out, the electroscope doesn't discharge with the magnesium plate on it as it did before.
So that's the demonstration. As you can see, it's actually a pretty simple experiment you can imagine doing. Now, in your setup, they are kind of all hidden inside the black boxes, so it makes it harder for you to see that. But what the measurements you'll be making of current, which you have to kind of trust your control box, is that's coming from this effect. So the first time people noticed that photoelectric effect was, I think, late 19th century. So when people were working with the light, they noticed this effect. As you can see, it's a pretty simple experiment. Once you kind of notice the weird thing, then people can do it. So, and it's almost tantalizing because you feel like you should be able to explain it. Let me just sketch what photoelectric effect involves. So in photoelectric effect, what you are seeing, or how you would explain what you see, like what you saw in the video, is you would say, okay, I have some metal surface on which some light is shining on. So you have light shining on it. And what you are observing, or how you explain what you are observing, is that as light shines on it, some electrons pop out, or you get, I guess something like cathode ray. You see electrons popping out of the surface as light shines on it. Now, just imagine you are someone, a physicist working in the late 19th century. So this is after development of Maxwell's theory of electromagnetism, and so you know about electromagnetic waves. And this is when a guy named J.J. Thomson have discovered the electron. I think he discovered in like 1890 something. So electron is known as a particle. People have been working the cathode ray tubes. So how would you explain what you are seeing here? Where would your first starting place be? Like, why would light interact with this charged particle in the first place? Is there something about light you know that you would say, oh, that should interact with the charged particle? Yeah, light is made up of electric and magnetic field. So what we describe as light, it's an oscillation of electric field and magnetic field. So, I could describe light kind of this way. It would look something like, wave of, or I was told to avoid saying wave because some people don't. So you have this so these arrows are representing electric field. And as light comes, this is oscillating back and forth. So if you have a charged particle sitting here, then as this electric field is oscillating, so on the very surface you have this electric field that's oscillating back and forth. That's going to cause this charge to feel a force due to this oscillating electric field. It's going to be shaken. You can imagine that this charge will, maybe as it's being shaken, it might gain enough energy to leave this surface. Right? So that's what I mean. It's so tantalizingly close that you feel like you have almost all the pieces you need for explaining this phenomenon, except that there were a couple odd things that you just couldn't explain. Let me just, so this is, I guess I can start out with what you saw in the video. So you can list 2 or 3 different things. The biggest thing comes down to this. This effect, this entire phenomenon is frequency dependent. Now, I don't know, does it make sense that it should be frequency dependent? So by frequency dependent, I mean, so this electromagnetic wave of light, if we made it higher frequency, shorter wavelength, then this would be, this oscillation would be happening at much greater frequency. Like it'll be flipping back and forth at double the rate it would in the red color when it's in the ultraviolet light. Like then just intuitively, like if you have electric field that's flipping back and forth more quickly, then does it feel like maybe this should gain more energy? Maybe, yeah. I mean, so it depends on your intuition. If you feel like, as it's flipping back and forth more quickly, then maybe this should shake more violently. Maybe. Now, so here's the part that you really cannot explain. It's, how do I explain it? It's what you saw in the video. So you saw with the visible light, absolutely nothing happening. And the visible light was pretty bright. And what I'll tell you now is that it didn't matter if you made that 60 watt light bulb, if you replaced it with a 600 watt light bulb. So let me qualify this carefully. So it's below a threshold frequency, it's intensity independent. By independent, I mean, it doesn't matter how much intensity you have. If you're below a threshold frequency of light, then nothing happens. Now, this is the part that you just can never explain with the wave model of light, because what does the intensity of light relate to as far as its electromagnetic property goes? So the magnitude of electric field, right? If you increase the intensity, you are increasing the, increasing this magnitude of the electric field. So, if you have a charge here, and if you apply large enough electric field, could you apply enough force to make it pop out? And when you do the analysis in classical mechanics, like you should be able to. Even if you were to look at what is the rate of change of electric field, well, you can keep the frequency the same. So as far as the rate of change of electric field goes, whether you double the frequency or you double the electric field or quadruple the intensity, they should work out the same thing because it's the same sinusoidal thing. You can make this slope steeper by either increasing the frequency, so decreasing the wavelength, or you can do it by increasing the amplitude. So this is really the biggest piece that you can't explain based on classical mechanics, or you cannot base. So this cannot be explained by thinking of light as electromagnetic wave, because if that's all the model of light you have, then it's a very puzzling thing that once you fall below certain frequency, that no matter how strong an electric field you apply, that the photoelectric effect won't happen. And on the flip side, if you have enough frequency, so as you reduce the intensity, what you would see is that you would see that the rate of discharge is slower as you reduce the intensity. But what you would see is that no matter how small the intensity, you would always get some discharge. So that's another thing that's kind of hard to explain. Like, if you reduce intensity enough, then are you just simply not shaking the electron enough that it would pop out? So I will say this puzzled people long enough, decades. So Einstein got his Nobel Prize 1921. I think I had to look it up while I was. They had some errors in the UC Berkeley physics lab, so historical errors. Physicists are not good historians, so I had to fix that. When did they say it last? I don't know, 1890 something. So for more than a decade, some people were studying it, and they didn't really have a good explanation. And well, chronologically, this comes first. So I guess, once again, physicists are not good historians. I don't know where Einstein got his inspiration, but it's oddly similar to this. So what Einstein hypothesized was, well, maybe when this electromagnetic wave interacts with particles, maybe there's some kind of minimum amount of energy that has to be transferred. So call that minimum change in energy. And this minimum amount of energy that has to be transferred is equal to Planck's constant, which comes from here, times the frequency of electromagnetic wave. So it's oddly similar to this, because if you're saying, let's see, So it's oddly similar to this. The difference being that here we are talking about the frequency of the oscillators. So these hypothetical oscillators, they are not even real objects because it's a way of modeling a black body. So it's something that's poorly understood. But electromagnetic wave is supposed to be something that's very well understood. There's a whole set of 4 differential equations that tell you exactly how it behaves. But Einstein was making this bold assumption that you could somehow generalize from this and say, well, even for this very well understood thing of electromagnetic wave, that this might be true. And in fact, I think he's saying a little bit more than this. So each time electromagnetic wave exchanges energy with the electron, so it's not enough to say that amount of energy exchanged is simply integer multiple of this, because if that was the case, this could get enough energy when you have low frequency of light. So really this is where you cannot avoid introducing this idea that light is a particle. That when you think of interaction of light with the matter, you have to almost look at it like a collision between 2 particles. So light is a stream of particles of a certain energy that's colliding with this electron. And if that stream of particles, each individual particle has enough energy to pop out an electron in a single collision, with a high enough frequency, then it would. But if in a single collision it couldn't pop it out, then before there's a chance for next collision, this electron would lose energy again. So this is where, like, if you are trying to avoid saying the word that light is a particle, you twist yourself into whatever jumble. So you end up having to say you are dealing with energy of a photon, which is the name we have given to this light particle. And energy of photon is Planck's constant times frequency of, well, I guess we are still treating it somehow like a wave, because like it wouldn't make sense to talk about frequency unless we are still dealing with the electromagnetic wave, right? Like, suppose I asked you this: what is the frequency of this still ball? Is that a valid question even? Not really, right? If you're talking about it as oscillator, it has some thermal frequency, then that's one thing. But if I'm telling you this, treat this like a point particle. It doesn't have any constituent parts, and what is its frequency? Particle doesn't have a frequency. Particle has a velocities, momentum, those particle properties. Waves have frequencies. So in this expression, you are containing those two seemingly self-contradictory quantities. So we are treating this light now like a particle, but at the same time we are doing that, we are not getting rid of any of its previous wave properties. We are still treating it like a wave. So this is the bold assumption that Einstein made, and he turned out to be right. There's a guy, so one of the things you can do is you can then not treat this like a collision between a particle and another particle. So you could say, you could say things like, so this is what your lab is about. You could say things like the maximum kinetic energy of the electrons that are popping out. Well, that must come from the energy of the photon. So that would be, Planck's constant times frequency of light. But, well, this electron is somehow bound to the surface. Under normal circumstances, it doesn't just spill out of the metal. So there must be some kind of potential energy, negative potential energy binding it. So you say, all right, so this is how much energy you are adding each time with each collision, minus whatever potential energy that you need to overcome first. And this is what's called work function in your lab. So this is a pretty simple, like a simple sort of analysis of what must happen based on collision of two things that have energy or can have energy. And once you have electrons that are popping out with some amount of kinetic energy, then you can think of some electrical arrangement to try to measure this. That's what your lab setup is. But this is a pretty simple prediction, and that you would have, I guess this is the prediction, that maximum kinetic energy of the particle popping out would be linearly dependent on the frequency, down to the threshold frequency, where you would have, I guess, zero maximum kinetic energy, that would be h times the threshold frequency. So this would be a way of figuring out what the work function is. So that's Einstein's theoretical prediction, surprisingly simple. Maybe because it's simple, somebody did do the experiment like a few years after Einstein proposed it, and like a couple years after, I think the experiment was done in 1916. And once you have a theory that's experimentally verified, now the Nobel Committee can actually give him the Nobel Prize that they knew had to give to Einstein at some point because he's a genius or something. So this is a photoelectric effect. Once you get over this hurdle of hearing that light is actually a particle, then it's actually mathematically pretty simple. Right? Everyone here okay with the idea that light is a particle? Yeah?
Is it the particle that's causing the wave, or do they both get emitted simultaneously?
Well, think about electromagnetic wave. So let's see. If you have, electromagnetic wave like this, I think I see what you're saying. So when we talk about sound waves, sound waves are actually made up of particles. It's made up of air molecules. But the air molecules themselves are not the sound wave. Air molecules simply make up the medium that the sound waves travel in. Now, what is the medium for this light wave? What did it say the medium for the light wave was?
Ether?
Well, we went over for 2 weeks how it doesn't exist. So what is the medium for the light wave?
Electromagnetic spectrum.
I mean, so what we call light wave is an oscillation of electric field and magnetic field. So, or it's a propagating oscillation of electric field and magnetic field. I can get electric field to oscillate by just taking a charged particle and shaking it, right? So this is the question. For this shaking of the electric field to propagate through space, does it need to depend on some kind of material medium? No, right? It can travel through vacuum. So light has no medium. Unlike sound, sound does need this air to travel through. If you vacuumed out all the air in the room, you wouldn't hear me. Well, aside from dying soon. So you are asking, okay, so then is it a particle that's making up the wave? Well, there's nothing material underneath the electromagnetic wave to consider as a particle. So that's the, does that answer at least some part of your question?
I'm just wondering if it's like the photon is somehow charged and that's what's creating something around it, or is it just like they're both?
I can tell you one thing. Photon has no charge. Yeah. So if you have a charged particle, something that's negatively charged, as I shake it, it's going to generate electromagnetic wave. But the electromagnetic wave itself, it doesn't have any charge. And you kind of know that because the one light wave doesn't actually interact with another light wave. If I cross these two in the middle, like they don't interact with each other. And in fact, this is why we get the whole superposition principle and all that stuff, because one oscillation of electric field doesn't interact with another oscillation of electric field. So I can tell you right now that this electromagnetic wave, it's not associated with anything that has an electric charge. So with the quantum mechanics, I will say this much. If as you hear the words I speak, if you thought, oh, that makes sense, then I will just warn you that you may not have thought it through too much, which is okay maybe for this class because it's lower division physics. But Feynman said these famous words. Richard Feynman, he did a quantum electrodynamics, whatever. That if you think you understood quantum mechanics, then you haven't understood it, or something like that. At some point, maybe not today, but as you are going through quantum mechanics, some aspect of it should cause you to puzzle. And I will tell you, with the special relativity, I said there is no such thing as paradox in special relativity, because it's just misunderstanding. With the quantum mechanics, there are paradoxes. There are unresolved questions, not of things that you can resolve by experiment, but more of what we call interpretation of quantum mechanics. So let me just leave you with this. 9 formalisms of quantum mechanics. I think that's the name of a paper. 9 formulations of quantum mechanics. So I think I did say at some point, quantum mechanics has a traumatic childhood, right? And this is one aspect of it. There aren't 9 formulations of special relativity. But with the quantum mechanics, there are many different ways of expressing it because there are aspects of it that just deeply disagree with our classical intuition, and there's no easy way to simply explain it. Here, use this Lorentz transformation, and everything will be fine. There's nothing like that for quantum mechanics. So what I want to do starting today is to introduce you to some of the quantum mechanical assumptions, quantum mechanical things that, I introduced this by saying this was an ad hoc assumption. And things are going to get less ad hoc. we are going to have more fundamental assumptions, things that's universally applicable. But it'll still be an assumption. It's not something you can derive from classical mechanics. It's something new that you have to be told. Okay? So I think that's enough to move on to something new that you have to be told. And that's what's called de Broglie hypothesis. And I don't want to spend too much time on de Broglie hypothesis. I'll just quote unquote drive the expression. So, by the way, I think he's a French physicist. I'm just never going to pronounce. Does anyone here speak French, by the way? No one here does? I keep asking every semester. I don't know how to pronounce this. I say de Broglie because when I try to say de Broglie, I can't really say it right. If someone knows correct pronunciation, teach me. I'm just going to say de Broglie. So de Broglie hypothesis. This he actually got Nobel Prize for his PhD thesis where he introduced this, which is probably why a lot of physics theorists have a bad habit of introducing unjustified or some whatever. So what this is what sort of a short version of what de Broglie did. He looked at what Planck did, assuming this. He looked at what Einstein did, taking this assumption and applying it even more broadly than Planck himself would have felt comfortable doing. And he looked at it and he thought Einstein didn't go far enough. He thought he should have gone farther. He thought that, so this is a basis of what we call, what your lab manual calls wave-particle duality of light. And de Broglie, this is the short, very abbreviated version. He looked at it and he thought, Einstein didn't go far enough. In fact, he didn't have to say of light. He made this assumption, hypothesis, that this wave-particle duality exists with everything. For example, if you have this, I was asking, what is the wavelength of this? De Broglie would say that, yes, this does have wavelength. And we can actually assign a wavelength to it. And the way it's experimentally verified at first was, so based on the expression relationship that he guessed that, you can come up with a wavelength for electrons and protons under certain circumstances. And you can do an interference experiment with these, electrons, protons, and neutrons. And when people did the Young's double slit interference experiment with electrons, they got the result that's consistent with the wavelength predicted by this de Broglie hypothesis. And you can actually get the relationship he was guessing at from here with judicious substitutions, and because this is, I guess, somehow a universally applicable relationship that we just have to do some correct algebraic manipulations and substitutions to get rid of anything that's specific to light. So let's just start out with this. We have energy of electromagnetic wave, or I guess I should really say energy of photon is equal to Planck's constant times frequency of the EM wave. So Planck's constant, we are going to keep it in the end. And as we go through quantum mechanics, you will see this constant as the surefire hint that there's something quantum mechanical going on. So I'd like to rewrite the energy of light into something else so that I can quote unquote derive an expression that's more universally applicable than light. How would I do that? Well, energy of light, actually this is the total energy because there's no mass. So you are thinking of this, right? In special relativity, you have this energy momentum relationship. The total energy squared is equal to the rest energy, or the thing that's based on rest energy plus PC squared. Right? With the light, there's nothing material there that you can slow down and measure. That's a rest mass. So with light, you can say that this is 0. And in fact, well, this looks like a valid expression, right? E squared is equal to PC squared, or energy is equal to momentum times C. Like, I'm not dividing anything by 0. I'm not multiplying anything by infinity. Seems fine to me. And this is actually a valid expression. So anything for any particle that's massless, you have this relationship that its total energy is momentum times C. And that's true of light. So this, I can replace it with, all right, energy of photon is the momentum of photon times C. All right, I don't think I really like this C because speed of light kind of seems specific to light or special relativistic circumstances. And I'm hoping that this can apply to something that's non-relativistic, that I can get rid of this C somehow. So on the right-hand side, I see I'm running out of time, so let me just go through this quickly. I see this frequency, which I can rewrite in terms of speed of light. So you have this relationship. The speed of a wave or speed of light is equal to wavelength times frequency, right? People remember that? So this, yeah, all right. So frequency, so solving this for frequency is equal to C over lambda. So plugging that in, what you have is H times C divided by wavelength of electromagnetic wave. And once you get this far, then that's where you see that anything that's specific to light wave gets canceled out. So C gets canceled out. And when I was keep asking what is the frequency of this, it's like, what's the phrase? What's the frequency, Kenneth? Some popular thing, I don't know, whatever. It's hard to say what the frequency could be, or what kind of experiment you do to measure a frequency. But if we are talking about wavelength, then there's an experiment you can do to measure it. Young's double slit interference experiment that actually measures wavelength directly. So you have this. Momentum of photon is equal to Planck's constant divided by wavelength of the photon. So this is where de Broglie makes the bold jump that it makes. So far he hasn't introduced anything new. What he would now introduce is that he would say, well, we don't need this, that this is a universal expression, that this relationship applies to everything. It applies to light, obviously, and it applies to this ball. So let me just copy it over. He would say momentum is equal to H over the wavelength. This is what we are going to call de Broglie relationship. Because I'm not calling it hypothesis anymore because he turned out to be right. Somebody did this experiment. So, momentum, it's the regular old momentum. If you're doing non-relativistic measurement, then this would be just the mass times velocity. So if you have something that has a mass, and if I throw it up, then it has velocity. Then it has a wavelength. So if let's say I drop it, and let's say it's moving down at 1 meter per second, then I can calculate its wavelength. So wavelength of this thing as it's dropping, and let's say it's moving at 1 meter per second, its wavelength would be, move over here. So it will be h over momentum. It will be Planck's constant divided by momentum, or h over mv. And what do you think that number will turn out to be? Small, large? Small. Yeah, it's actually fantastically small. Let's say this is, I don't know, let's say it's 10 grams. 10 gram mass moving at something like 1 meter per second. If you plug in the numbers to get what the wavelength is, it's fantastically small. All right, let me just plug in the numbers. H divided by 10 grams times 1 meter per second. I should get something of length, hopefully. Oh, hour, that's not right. Oh, Is Planck's gone? Okay, so 10 to minus 32 meters. Do people know the scale of small things? What's the smallest thing you know? Well, that's a prefix. But what do you know physical stuff? That's femtometers big. So femto is what, 10 to minus 15? Or 14? Well, so angstrom is 10 to minus 10. Anybody here know what things are over an angstrom in size? Atoms, yeah. Size of an atom is 10 to minus 10 meters. Atomic nucleus is 10 to minus 14 meters. This is much, much smaller than that. And this is actually our explanation of why haven't you noticed this before? Well, for a macroscopic object, it's such a fantastically small number that whatever effects of interference or diffraction you might have tried to measure, you wouldn't have seen it. But the picture changes when you are dealing with the microscopic objects, because then this mass becomes much smaller. When you are dealing with the electron, let's say I have an electron that's moving at 1 meter per second, which is actually super slow for electron. But if I'm now dealing with electrons, electron mass, by the way, it's really hard to get electrons to move that slow. It's a really cool electron if it's moving that slow. It has a wavelength of, wait, what? Electron mass as a unit, maybe. No persistence. All right, 10 to minus 4 meters, or about a millimeter. That's something you can measure macroscopically. And I don't think the experiments did have it. Anyways. So, so once you have microscopic things, that's when you can notice these effects a lot more. That's why sometimes you hear this expression that classical mechanics deals with a low speed. You now know why after we've done special relativity. Low speed macroscopic objects. Special relativity deals with when things are moving fast, speed of light or something close to it. And quantum mechanics, people say it deals with microscopic small things. It's because the quantum mechanical effect, they only become apparent when your momentum is small, which is a lot easier when your mass is small. Yeah.
I think what I said I would first describe is the uncertainty principle. And I have some figures here, which is meant to kind of illustrate that. But these fixed figures can be a little bit not very proficient at what we mean by uncertainty. So let me use one of these simulations from pet.colorado.edu to illustrate that. I think the one that I want to use is this one, quantum wave interference. This can both be used to illustrate what we mean by uncertainty. For example, uncertainty in position. That's probably the easiest thing to describe. So let me start out with that, and I think we might be able to even get to interference. All right, so this is the simulation. Do I want high intensity? Well, we can do high intensity, but I don't think that has really a context for us to think about. You could think about this as like a beam of light. Am I doing light? Well, yeah. So all these particles here have both a wave and a particle nature. That would be what we mean by the wave-particle duality. So I think let me just stick to photons, which are particles of light. We have already talked about light as wave, and now what we are saying is that this light has particle nature. And I think it's easiest to describe the particle nature in single particle mode. So let me get to that, single particle mode. So, all right, so this is what you have to imagine. This is my source of the light particle. It's a light source. And I guess what you have to imagine is that it's a source whose intensity I can control so well. Most specifically, I can send such a low amount of light that when I send some light, I have some assurance that only a minimum possible amount of light is being sent. You might say a single photon of light is being sent. And on the flip side, what I would have to say at the top here on the screen side, I would have to say I have detectors that are so efficient, so proficient at detecting light that if a single particle hits this detector here, I would detect that single particle. If that single particle hits detector here, I would detect a single particle. And there are actual, this is not entirely theoretical. There are actual real-life experimental devices called photo multiplier tubes, which can actually be used to detect single photons. And I guess from my experience with the high intensity, what I might expect is that as the light hits, if this is my beam width, then the light could be anywhere there. I guess if I maybe reduce the intensity, I might see a bit of a kind of dimmer thing, so it's not all saturated. But you can see the width of the beam spot, and the light may fall anywhere here. So let's look at with a single particle what happens. So I fire a single particle. Ignore that. So on this entire screen, I don't have a distribution of light. When I look at this detector that's able to detect a single particle, it says it detected a single photon, and it detected it here at this very arbitrarily small location. So, all right, you feel like, and that's not even at the center, you feel that's weird? Okay, let's just fire a few more photons. Thought I could do this faster. Okay, rapid. Okay, so that looks maybe a little bit better. My photon is over there, but it's still at a single point. It's not spread out. So now what you can do is you can fire it repeatedly. And each time you fire a photon, each time you detect it, you will see it detected as a single particle. And that's what this figure was illustrating. The figure here was illustrating when you have only 40, okay, here it's electron. When you have 40 electrons, those particles are detected like this. So when am I going to see a picture that resembles this better, where I have a spread out distribution of intensity, and it kind of looks like a light from light wave. Turns out if you fire this enough, so you have an enough number of photons on that other side to basically build up significant enough statistics, that's when you begin to see a pattern that resembles what you see in high intensity version of the simulation. You see that most of the particles are clustered around the center. There are a few odd ones that are kind of outside of the center, but for the most part, they are in the center. So yeah, that's so that's what we refer to. That's what we refer to position uncertainty. It's uncertainty in this very specific sense. When I fire this photon, it can be kind of anywhere in the screen. Now, I don't mean it can be literally anywhere, as in all the points have equal probability of receiving a photon. What you really have is a narrow range has a greater probability, and outside of range, you have a smaller probability. And within that constriction, when you find a photon within this smaller range, they always show up as a single particle. but their position uncertainty before I detected it was about width of the beam that you would see with the high intensity beam. That's the uncertainty of position, because each time you fire, the position could change. It doesn't have to be there. Now it's here. But what you will see is that as you fire this multiple times now, you do have far outliers. That happens. Nothing's wrong with that. But if you have collected enough data, if you have a statistically significant number of photons being detected, then those photons are mostly around in the central, what we call central maximum. And you might just leave it that at, okay, that's odd, but I think that kind of makes sense. If it's particles coming out of this beam, then as they are coming out, it might be striking something else. Angle could shift a little bit, so it makes sense that most of the particles fall within this range. And all right, everything explained. Let's move on. The thing that stops us from doing that is the interference effect. So it's a kind of an interference effect that we didn't talk about when we did the waves, but it's something you can see here. I'm doing what's called a double slit interference. So you have this light wave coming in through one slit, coming in through the other slit, and you see a bit of an odd pattern on this other side here. And this is what it's showing. You see this line of points where you have no light or very little light. That's where you are seeing what we call destructive interference. You have seen examples of destructive interference with the nodes of standing wave. And it's also similar here, although I guess you can't quite describe this as standing. So, this is destructive interference. That's a phenomenon that's distinctly unique to waves because it requires a superposition principle. I mean, imagine this. Imagine you had an electron and you add another electron to it. Would you expect to get 0 electron? That makes no sense at all. And if that were to actually happen, that is inconsistent with the conservation of energy. So we're not gonna go there. But when you have two waves, those two waves can be set up in a way that they destructively interfere. When one goes up, the other goes down. And that's what this black band is describing. It's showing the positions where the screen can be placed, where those light waves from one slit and the other slit destructively interfere. So there's one here, there's one here. There ought to be one there and there, but yeah. And this is what you might see literally in an experiment, working with the lasers and double slit. We do this lab in physics 4C. It's a lot of fun. Now, when we repeat this experiment with the single particles, what do we expect to see? That is the question. This is what you see. So you remember this picture, high intensity interference pattern. When you fire single particles, it'll look like nothing is happening or nothing different is happening because you see a particle there. It was kind of within the range of the medium, and all right, that so it looks like the barrier didn't do anything, but continue firing because what you learned earlier is what you see with a single measurement may not accurately represent the physical picture. When you continue to fire it and you build up a statistically significant sample size, I want to point out what you will see. I want 1, 2, 3, 4. Okay, I think maybe I can do this 20-ish more times and the pattern I'm looking for will become visible. Do you see a pattern yet? Yes, no, maybe. I think that's good enough. You might be beginning to see the pattern. So what I want you to realize that each time a photon falls, you can't really predict it where it'll land. it might land within this range, it might land within this range or this range, but I don't know where to, like with the next one I'm gonna fire. Let's see, it landed here, but I had no idea it was gonna land here there. It could have landed in the middle. It could have landed on the left. With the next one I fire, it landed in the middle. So this is what I mean uncertainty. When you measure the position here, there is uncertainty. But within that uncertainty, look for a pattern here. Do you see anything unusual, possibly interesting here? I hope you are beginning to notice these dark bands where no photons or very little photons appear to be landing. And when you kind of switch back and forth between high intensity and single particles, I hope you see a correspondence. Where you have dark high intensity, which means the phase of the two electromagnetic oscillations are just the right amount to cancel each other at that spatial point. And with the exact same setup, exact same everything, in the single particle, you are seeing this same exact feature open up again. So yeah, that's our evidence for the still remaining wave nature of photon. So in the earlier discussions, we had people choose, is light photon, or is light a particle, photon, or a wave? The insistence would have been, it couldn't possibly be both, it's one or the other. And what we are learning in quantum mechanics is that that one and the same particle, photon, can have both wavelength and momentum. So this is what we mean by uncertainty. So uncertainty in position. And here the uncertainty momentum is a little bit harder to see. It basically has to the component of momentum that's going in a direction parallel to the screen, but let me leave that there. All right, so I hope this helps you think through the idea of uncertainty.